If you look at the way drugs used to be discovered, more often than not, you'd find that it was very much a matter of trial and error. A detailed understanding of their mode of action only came afterwards. Nowadays, in developing new drugs, pharmaceutical companies tend to begin by investigating the biological mechanism right from the start. Why? Well, drugs often contain one or more chiral centers, and hence exist as mirror image forms, or enantiomers. Because they're easier to make that way, they're often used as a 50-50 mixture of the two forms, a so-called racemic mixture. Because nature is chiral, the effect of the two isomers in a racemic mixture are often different. At best, one isomer may simply be ineffective. But of more serious concern is the possibility of different side effects. The drug thalidomide, used during the 1960s, provides the most widely known instance of such a difference. It has a chiral center, but in common with nearly all other drugs used at the time, thalidomide was administered as a racemic mixture. When taken as a sedative by pregnant women, thalidomide was found to damage the fetus, with effects that are only too well known. It was only later that metabolism studies showed that these effects were probably caused by just one of the isomers. Nowadays, toxicological evaluation is very much more stringent, and pharmaceutical companies in future are more likely to submit a single enantiomer for testing rather than a racemic mixture. Consequently, there's a great deal of current interest in methods for synthesizing single enantiomers, in other words, chiral synthesis. Until the 1970s, most attempts at carrying out a chiral synthesis were not very successful. However, in recent years, several methods have been developed for carrying out synthetic transformations with very high enantioselectivities. In this program, we're going to look at the race to find such chiral reagents. One series is based on the chemistry of organoboron compounds pioneered by Professor Herbert C. Brown at Purdue University in the USA. Among the more successful such reagents are organoboranes based on the naturally occurring substance alpha-pinene. Dr. Clint Lane works for Aldrich, who manufacture these reagents.
Well, the first chiral organoborane reagent that we offered was alpine borane. Alpine borane is made by the hydroboration of alpha-pinene with 9-boro-bicyclo-331 nonane, a reagent that we offer, our so-called 9-BBN. Alpha-pinene is readily available in both plus and minus forms. It's isolated from turpentine by distillation. Turpentine is available worldwide in various purities, and depending upon where the trees are growing and what pine trees that it comes from, it can either be predominantly plus or predominantly minus.
Individual groups of pine trees may well only give rise to a single enantiomer of alpha-pinene. However, the turpentine comes from a mixture of trees. So the resulting alpha-pinene, though largely one isomer, also contains some of the other, so must be enriched.
We are able to clean up the alpha-pinene and make it even higher optical purity by a hydroboration, dehydroboration process using diisopynyl camphene borane, and make alpha-pinene that's 100% optically pure. This makes the reagents, the chiral organoboranes, then readily available either plus or minus in 100% optical purity.
Since both the plus and minus isomers are readily available, both isomers of alpine borane can be produced with 100% optical purity by this enrichment process. What we end up with are asymmetric reducing agents that will reduce unsymmetric ketones to optically active secondary alcohols. Such chiral alcohols are increasingly used as pharmaceutical intermediates. For example, alpine borane made from plus alpha-pinene reduces acetophenone to give predominantly the S isomer of 1-phenyl ethanol. So, why is the S isomer so greatly favoured over the R isomer in this case? To understand why, we need to look at the transition states for the two possibilities. This is the transition state for the formation of the favoured S isomer. The most striking feature is that it involves a fairly rigid cyclic structure. This is a characteristic of all successful chiral reactions, tight control of the spatial environment of the reacting groups. The group that exerts this control, here the isopeno-camphale group, is called the chiral auxiliary. In this transition state, the methyl group, which is the smaller of the two ketone substituents, is adjacent to the methyl group on the chiral auxiliary, while the larger phenyl group is orientated well away from any other groups. In contrast, in the other transition state, the one for the formation of the unfavoured R isomer, the phenyl group is brought close to the methyl group on the chiral auxiliary, giving rise to severe steric repulsions. Alpine borane reduces acetylenic ketones, alpha ketoesters, and haloketones with very high enantioselectivities, approaching 100%. But with other, less reactive ketones, alpine borane is much less enantioselective. Attempts to develop a more enantioselective reducing agent led to another chiral organoborane compound called di-isopenocamphale chloroborane, or IPC2BCl for short.
Well, the diisoprenylcamphale chloroborane is one of the more recent reagents, and it is shown to be more versatile. It has wider application for ketone reductions, and in many cases it also gives high enantiomeric excess. A specific example is the aryl alkyl ketones, and there are some pharmaceutical intermediates that have this structure that there is a lot of interest in these type of products on a commercial scale for in drug synthesis.
One example of the improvement obtained with the new reagent is the reduction of acetophenone. It gives the product alcohol with 98% enantioselectivity compared to 78% obtained with alpine borane. Why the improvement?
There must be an electronic effect that the chlorine withdraws electrons from boron and makes it even more positive than it already is, so you get a better complex. There probably is also a steric effect because when fluorine, chlorine, bromine, and iodine were evaluated, things just didn't quite all make sense from a purely electronic effect, so there probably was some steric effect also. But the bottom line is, for a practicing organic chemist, the chloro works, the chloro is available, and it's also inexpensive, so it satisfied all of our needs.
Diisophenocamphale chloroborane and alpine borane are reducing agents. But organoboron reagents are much more versatile than that, and a vast array of other reactions have been developed over the past 30 years. This means that, in principle at least, these same reactions can now be used to synthesize chiral products. All these reagents involve the use of a naturally occurring chiral auxiliary. But there is another approach. It's based on this molecule, chiral iron acyl, and consists of an acyl ligand attached to an iron chiral auxiliary. It was invented at Oxford University by Dr. Steve Davies.
In order to achieve asymmetric synthesis, you actually have to control the three-dimensional space very precisely around a given reaction site. If you can do that, then you automatically achieve good asymmetric synthesis. So we set about trying to design a completely artificial system that would allow us to achieve this very precise control. We've done that using transition metal chemistry. It has the added advantage over standard organic chemistry that the complexes are generally octahedral in nature. So you have 6 rather than 4 ligands around the central atom. The bond angles are 90 degrees and all the groups are very close together. So if you're looking for precise control over three-dimensional space, then that obviously gives you a better chance of achieving it.
The chiral iron acyl reagent consists of an acyl ligand, which is the reactive center, attached to an iron chiral auxiliary. The chiral auxiliary consists of an iron atom to which are attached various ligands. These are a cyclopentadienyl ligand, a carbon monoxide ligand, and a triphenyl phosphine ligand. These ligands exert the required three-dimensional control around the reactive center, the acyl ligand. This is achieved because the acyl, here an acetyl ligand, interacts with the triphenylphosphine. Interactions with one phenyl ring force it to lie close to the plane formed by the iron, carbon monoxide, and acyl carbon. In addition, interaction with a second phenyl group orientates the acetyl within this plane such that the acetyl oxygen is anti to the carbon monoxide. Thus, the triphenylphosphine orientates the acetyl group. Not only that, it also effectively blocks one face of the acetyl. It must be appreciated that the triphenylphosphine is not a static ligand, but is freely rotating about the phosphorus-iron bond. The steric interaction of the acetyl and phenyl rings means that as it rotates, it's best imagined as a roller coaster, such that there is, on average, always one phenyl below the acetyl and another interacting with the acyl oxygen. All the elements are now set to achieve efficient asymmetric synthesis. The acetyl is oriented in three-dimensional space, and one face is blocked such that reagents and reactants can only approach the acetyl-methyl from one direction. As with the organoboranes, the essential feature is the tight spatial control exerted by the chiral auxiliary over reactions involving the acyl group. To simplify the reaction schemes, from now on, we shall represent the iron atom and the other groups by the symbol R star. How are these reagents used?
We were looking at general carbonyl chemistry. So the first thing we tried was to make a simple enolate from the acyl complexes. Now, in fact, since you have the equivalent of a methyl ketone, before you generate a chiral center, you have to introduce two substituents. When you introduce the first substituent, you're not introducing a chiral center. But when you introduce the second substituent, you do generate a new chiral center.
The first step is to react the acetyl group with strong base to form the corresponding enolate ion. This reacts with an alkylating agent, such as iodoethane, thereby attaching the ethyl group to the alpha carbon atom. The process can now be repeated using a second molar equivalent of base to give the substituted enolate. Reaction with a second different alkylating agent, such as iodomethane, then results in the creation of a new chiral center, adjacent to the carbonyl group.
And when we do that, we find we have essentially complete control over the absolute stereochemistry of that new chiral center. We can't detect any of the other diastereoisomer at this stage in the reaction mixture. And the absolute stereochemistry of the chiral center that we generate in this way is only dependent upon the order in which we add the two groups onto a given chirality of the iron reagent. So it's very versatile. Well, apart from the enolate chemistry, we can control virtually any reaction that's associated with a carbonyl group. And probably the next best example would be Michael additions onto something as simple as, say, the crotonyl group when it's attached to the same chiral auxiliary. Again, the auxiliary is essentially orientating the alpha-beta unsaturated carbonyl ligand in a particular way. The oxygen again stays antiperiplanar to the carbon monoxide, and the alpha-beta unsaturated acyl is restricted to lie in a cisoid conformation, again by the steric nature of the iron auxiliary. The triphenylphosphine blocks easily right out past the beta carbon of the alpha-beta unsaturated acyl, and thus the nucleophile, when you add it, must come from the unhindered face and generate the first chiral center. That then generates an enolate on the alpha carbon, and then again the electrophile, as you saw, in the enolate reactions must also come from the unhindered face, and that generates a second chiral center. Both centers are formed with complete control over the stereochemistry, over the absolute configuration.
Nucleophilic attack on an alpha-beta unsaturated carbonyl moiety, such as this crotonyl group, will preferentially occur at the beta carbon. Here, butyl lithium is not acting as a base, and conjugate addition occurs, generating a chiral center. Again, the bulky chiral ion auxiliary has controlled the direction of attack. So instead of a racemic product, a single enantiomer is formed. The resulting enolate ion then reacts with an alkylating agent, such as iodomethane, to give a second chiral center, again with a single enantiomer as the product. So, both chiral centers have been formed with complete control of their stereochemistry to give just one of the 4 possible isomers.
There's an alternative approach to the synthesis of homochiral molecules, and that is you actually take your chiral reagent, which for example would be the iron acyl enolate, and react it with something that is already chiral but racemic. Something as simple, say, as propylene oxide or as phenethyl bromide. If you do that, then you can still get homochiral materials from the racemic substrate you add. This is, if you like, a kinetic resolution type process and relies on molecular recognition. You're asking the reagent not to make chiral centers, but to recognize the difference between the configuration of one substrate molecule against another. So, for example, in the phenethyl bromide reaction, if you take the R enolate configuration, it can tell the difference between the R and the S configuration at the secondary bromide in phenethyl bromide. It does a simple SN2 substitution reaction, but it only does that on the R configuration of phenethyl bromide. It does not touch the S configuration.
It works like this. Take, for example, a racemic mixture of phenethyl bromide. Normally, both forms would react with an enolate in a nucleophilic substitution, giving a racemic product. But here, the steric influence of the chiral auxiliary, R star, is such that the enolate reacts only with the R isomer of the phenethyl bromide, leaving the S isomer unreacted.
In fact, it's even better than that, because the bromide you release in that first SN2 reaction goes around and racemizes the essentially kinetically resolved S-phenethyl bromide, turns it back into the racemate by repeated SN2 reactions, and produces more of the R enantiomer for the enolate to react with. So that you can actually add one equivalent of the enolate to one equivalent of the racemic bromide, and the final reaction product is as if you put in completely R configuration phenethyl bromide. You get a single diastereoisomer product out that is an SN2 reaction on the R bromide. If you like, it's molecular recognition and self-racemization in the reaction media.
So, as the R phenethyl bromide is used up by reaction with the enolate, the bromide ions released in the reaction then cause racemization of the remaining phenethyl bromide. Some of the excess S isomer is thereby converted into R. The end result is complete conversion, as if you had started with 100% of the R phenethyl bromide.
Now, at the end of the day, we've done an asymmetric synthesis or whatever with the ion chiral auxiliary still attached to the organic molecule. We generated the chiral centers with a high degree of control, but the molecules are useless as such because the ion is still attached. We've developed very efficient decomplexation methods that are very simple. They rely on one electron oxidation reactions in the presence of a nucleophile to generate then a normal carbonyl derivative. So if you oxidize in the presence of water, you get a carboxylic acid. Presence of an alcohol, you get an ester. Amine, you get an amide, etc. So you have a range of carbonyl functionalities that you can turn your ion group into at the end of a reaction sequence.
Both the organoboranes and chiral ion acetyls enable single enantiomers to be synthesized in high purity in the laboratory. But much of the interest in such chiral reagents comes from their potential for use in the pharmaceutical industry. So, just how feasible is it to use these reactions for the synthesis of chiral drugs? What factors have to be taken into account in scaling up to production size?
We generally do these reactions when we're doing our exploratory investigations on the 100 milligram scale. That's enough to isolate the product and do full characterization. When we developed a method, a general synthetic method for a particular type of final product though, we always scale the reactions up at least to a gram scale and often to 10 or 20 grams. The reactions are always the same on the larger scale as they are on the small scale, and therefore there's every indication you could do them on whatever scale you liked without any loss of stereochemistry or yield or anything.
There's always problems in scale-up when we take a reaction that's been reported in the chemical literature. Nowadays it's millimole scale and micrograms. So there's always a scale-up problem, and these scale-up problems are not unique for organoborane chemistry.
The reagents are very stable materials. We regard them as road-building materials. They're not like general organometallic reagents, which are regarded by organic chemists as air-sensitive, catch fire, etc. These are very stable. We've had material out in the open air for 8 years with no deterioration whatsoever. They're very easy to make, very cheap to make, and in fact they're now being made by British Petroleum Chemicals in Hull on a large scale and marketed, sold to the general chemist.
The organoboranes and the iron acetyls are but two types of chiral reagent among many that are currently under development. It's clear that after a long period of gestation, when the principles of chiral synthesis were known but could not be put into action, progress in recent years has been remarkably rapid. The ability to tightly control the spatial environment around a reaction site has long been known in nature to be the key to the action of enzymes. With the development of efficient chiral reagents, such as the organoboranes and the iron acetyls, organic chemists can now challenge and compete successfully with enzymes at their own game, not just in the laboratory, but also on an industrial scale.